Hello. So what we talked about in our latest lesson was kinetic. We started talking about kinetics of rigid body. So we talked about kinematics of rigid bodies. So meaning that we talked about velocity and acceleration of rigid body, how we can use body attached frames to describe the equation of motion, the velocity and acceleration equation. Sorry, not the equation of motion. And then we talk now, and then in our latest lesson, we talked about kinetics of rigid bodies, meaning that we said that, all right, so what we are going to do is we're going to start with the equation of motion for system of particles, and then from that, we're going to expand that for rigid bodies. So the translational equation of motion was sigma f is equal to mr double dot g, and r double dot g is acceleration at the center of mass. Then we had also sigma mg, the moment about the center of mass, and that's equal to the time rate at which angular momentum about the center of mass changes. And then what matters here, and was really different for rigid bodies as opposed to system of particles, is angular momentum. For angular momentum, for system of particles, we had this thing. We had for system of particles, we had this angular momentum, and this was equal to sigma our h for a system of particle was equal to sigma I equal 1 to n ri prime cross mi vi prime. This was for system of particles. Now we said that if we decompose a rigid body to many particles, then we can expand this relationship and use it for a rigid body. The difference would be, as the number of particles increases, we know from our calculus that this sum should be replaced with an integral over the entire body. So that sum is replaced with an integral over the entire body. All right. And then we also talked about the fact that, all right, for a rigid body, we said that this vi prime, which is the velocity of points in our body attached frame, has two components. One component was ri prime circle, which was describing the change in magnitude of ri prime, and the other component was omega cross ri prime. Remember? So, and then we said that the first component goes to 0. Why? Because the first component describes a change in length of ri prime. And for a rigid body, by definition, the distance between each 2 points, in this case between origin of body attached frame and an arbitrary point in this rigid body, this distance remains unchanged. So the first term in that vi prime goes to 0, so we end up having only omega cross ri prime. So this term, vi prime, is replaced with omega cross ri prime, and the sum is replaced with integral. And our mass, mi, now is replaced with our dm, and we said dm, it describes or represents small masses in this rigid body. All right. So then we need to integrate over the entire body. Now, we said that if I explain that, if you look at this equation for angular momentum, you see essentially two types of variables, meaning that we have one ri prime and dm, which depends on mass distribution in this rigid body, right? Ri prime and dm do not depend on our motion. They don't change with our omega, right? So the translational motion the rotational motion of rigid body does not affect Ri prime and dm. So what we're going to do is then, based on that, what we're going to do is we're going to use a mathematical identity, replace this cross product with this two terms in the bracket, and we can also replace dm with rho dv, rho being density, and dv now is a small volume in this rigid body, and then expand this expression and find what's called inertia matrix. So note that, alright, so Ri prime represents position vector, right? Position vector has three components, x, y, z in its most general form. So if you replace Ri prime transpose with x, y, z, Ri prime with x, y, z, and I is our unit matrix. And again, this is a math identity. We replace cross product with these terms. And then we have Ri prime x, y, z and R prime transpose multiplying rho dv. So, and this whole thing, excluding omega, is our inertia matrix. So if you are interested in the proof, you can simply expand this expression and show that you can have this inertia matrix, and each of these terms are expressed in terms of x, y, and z. So for example, I, z, z, or for example, let's say ixx, and then we look at izz. So ixx is equal to xs. You can actually already get, just by looking at this equation, you can guess what ixx could be, right? Because you have x multiplying x, because you are only interested in the first component of this inertia matrix. X multiplying x gives you x squared plus y squared plus z squared, but then second term gives you minus x squared. So you have x squared plus y squared plus z squared minus x squared. So you get ixs equal to y squared plus z squared rho dv. And the integral is performed over the volume. And you can easily show what are each of these components are equal to, right? So, and just one more thing about this matrix. Ixx, Iyy, and Izz are bodies, mass moments of inertia. Right? I just say moments of inertia, it's common. You can also call mass moments of inertia. And the off-diagonal components, these components are called products of inertias. Right? So, for example, this term, Ixy, is equal to integral xy rho dv. Right? And you can compute, so my suggestion is to practice, you can expand, you can do this, you can expand these terms and compute each of these components. All right. And you should also notice that, you should have already noticed that this is a symmetric matrix, meaning that these two components are equal to each other. Right? So, pay very close attention here that the mass moment of inertia, or the inertia matrix, does not depend on your kinematic variable. It does not depend on your angular velocity vector or translational velocity or translational acceleration. So it's a property of the body. It depends on mass distribution. And as long as this mass distribution is fixed, and you keep your reference frame attached to your center of mass fixed, right? Pay very close attention. So it depends on this. This description depends on that frame. This Mass moment of inertia does not change. Now, let's say for our special case, because what we are interested in this course is planar motion. So if you have a planar motion, what happens? If I have a planar motion, my omega for planar motion, so planar motion, for planar motion, our omega is only going to be equal to, omega is only going to be equal to what? It's only going to be equal to, and let's say I have my body rotating about the z-axis. It doesn't make any difference if you assume it rotates about x-axis or y-axis. Let's say it only rotates about z-axis. So if it only rotates about z-axis, how many non-zero components do we have for omega? So it only rotates about the z-axis. So the x component is going to be 0 because we are not rotating about x-axis. The y component is going to be 0, and the z component, let's replace the z component with omega z. Great. So now if I go back to my angular momentum here, all right, so if I replace my Ig with this Ig and my omega with this omega, so the only term I would be interested in, the only non-zero term would be Izz, right? So if I multiply, so if it is hard for you to do this, to do it in your mind, so what you should do is just write down this matrix, pre-multiply this vector with this matrix, and you could see this. You can see that our planar equation, planar rotational equation of motion is going to be equal to m about z equal to Izz omega dot z. Okay. So what did I do here? So I simply differentiated my angular momentum with respect to time. Remember? So if I differentiate my angular momentum with respect to time, Izz, again, Izz does not depend on time. It depends on geometry, depends on the mass distribution in our body attached frame. So when I differentiate this with respect to time, h with respect to time, this h, I only end up differentiating my angular velocity with respect to z. So I have Izz omega dot z. And if you want to describe the whole motion of this rigid body in plane, or the planar motion, you should also add two equations for translational equation of this body. So if we are in plane, we have one motion or along x-axis. So let's say we are in xy plane, planar motion in xy plane. I have fx being m r double dot, and I'm going to use for c for center of mass, x. So the translational acceleration along x, and then I have fy, m r double dot c along y. So this is simply our translational equation of motion. It has three components, right? This is a vector equation. It has three components, x, y, and z. These are x and y components. And we are staying in plane, so we don't have any motion along z-axis. So these three equations describe the whole motion, the whole planar motion of this rigid body in xy plane. So for example, if we had a planar motion in xz plane, what would it be? So think about that. If you had a planar motion in xz plane, it means that your rotation is going to be about y-axis, right? So your rotation about y-axis means that your only non-zero, the only component of inertia matrix you're interested in would be Iyy, right? So pay very close attention. When we say we are only interested in Izz, in planar motion in xy plane, it doesn't mean other components of this inertia matrix is equal to 0. Inertia matrix is inertia matrix for this rigid, three-dimensional rigid body. But because our omega has only one component, about z, this component is the component affecting the dynamics of the system. Right? So we have this equation. All right, so one last thing here. So if I'm in xy plane, so my izz is going to be again, if you go back to this matrix, it's going to be x squared plus y squared rho dv. Or you can replace this with dm and simply say x squared plus y squared over m dm. Right? So now in xy plane, if I ask you, all right, so if I ask you to describe this in polar frame, what would you say? If I ask you to describe this in polar frame, you would say x squared plus y squared is equal to r squared, r being the distance to our origin, right? So in polar frame, you could say this is equal to r squared dm. Right? So now let's say if I define a hypothetical mass, and for my hypothetical mass, the total mass of my hypothetical mass is equal to the mass of this rigid body. So if the total mass of this rigid body is equal to m, then my hypothetical mass is also equal to m. But I concentrate this mass at a point as far as r from the origin. So I'm replacing this total mass m at a distance r from the origin. So because now I have a concentrated mass, this r is the same for every point, right? So you can take this r out, and I'm going to call this a specific r k. So this is equal to k squared dm. And we said that the total mass is, let's say, equal to m. This k is called radius of gyration. So k is called radius of gyration. Right? So if I give you radius of gyration for a mass, say I give you an arbitrary rigid body, but then I give you radius of gyration, and I say I have this planar motion, and this is the radius of gyration. I'm not giving you izz, I'm giving you radius of gyration. So what you're going to do is, you're going to compute izz using radius of gyration. So I apologize, so I just write it here, just so I don't need to use a second page. Izz is going to be k squared m. So if I give you radius of gyration, you square that, multiply m to get izz, and then you can use that izz for planar motion. So radius of gyration is a very useful concept in dynamics of rigid bodies, and we're going to use that in one or two examples. This was for today. Essentially, I did repeat what I had taught in my previous lecture, and added some more materials, and then next lecture I'm going to solve an example. All right, see you later.